In our previous lecture, we have qualitatively shown how the classical physics fails to explain the behavior of black body radiations. What we mean by that is if we plot the spectral energy density U nu d nu, we explain what spectral density is. It's the energy radiated by a black body per unit volume in the frequency range nu and nu plus d nu per unit time at a particular temperature T. So at a particular temperature T, let's say 800 degrees Celsius, we choose a particular frequency, let's say corresponding to red color, and then we choose a range slightly around it. So let's say we start from some 2 into 10 to the power 14 hertz and maybe 2.0001 into 10, some 2.01 into 10 to the power 14 hertz. So we choose this range, nu and nu plus d nu, and look at this energy range, how much energy is radiated by a black body per unit time, and that will be our spectral energy density. So if we did that, so we chose a frequency and then we chose slight range around it and then calculated how much energy radiated and plotted that for every such frequency. So we will have a new axis in this direction, frequency, and the spectral energy density. We will see, like if we did the experiment, we will get some data points. So this will be our U nu, D nu, and this will be our frequency nu, or the other way. We will have some data points for particular nu's frequencies. We'll have some U nu, D nu. If we plotted them, we'll get something like this, and so on. I mean, it depends on you, how much data you take. So if you take it some frequency value and another frequency value very close to it, then you would have, of course, more data points. It would look like this. So that's our black body radiation curve. We don't know what mathematical function this is, but that's how your measured data points look like, your experimental data, the ones that you do. I mean, if you had a black body in the lab, in our physics lab, if you did this experiment, it would look like this. For now, forget about the numbers, exact numbers, okay? Some numbers are here. Some 2 into 10 to the power 14 to 6 into 10 to the power 14 or something like that. Hertz in this way. Now, we have to, and we said that classical physics failed to explain this behavior. And therefore, quantum mechanics, and therefore Max Planck explained this, and as a result, quantum mechanics came into action. Today, I'm going to derive the exact function, U nu d nu, theoretically, the way Rayleigh and Jeans did to explain this behavior, and we'll show that how they failed. So anyway, remember, this is our curve. And what that means is, this curve has a particular peak value of frequency. So for example, if you heat up a piece of iron, it will be a piece of steel, it will be around 800 degrees Celsius. It will turn red. What that means is that it's radiating most of its energy in the frequency corresponding to the color red. But it does not mean that at that temperature it's not radiating blue, it's not radiating infrared, it's not radiating yellow. It does not mean that. It just means that it is radiating every frequency, but those are not dominant. They're very less amount of energy is radiated in those frequencies. At this temperature, this peak corresponds to red, okay, for a piece of iron, for example. If you increase the temperature, let's say to 1200 degrees, then you will see that now the piece of iron looks more like yellow. So at this temperature, most of the energy is radiated in this frequency that corresponds to the color yellow. But it's still radiating red, but the red now is not dominant anymore. It's lying on this side and it's radiating energy in red, but less amount of. So for a particular temperature, there will be a peak frequency. Actually, if you increased the temperature, the peak value of frequency tends to shift in this direction, and therefore, so which means if you increase the temperature, the frequency, the peak frequency will increase, and that's how, and that means peak wavelength corresponding to this frequency will decrease. So peak wavelength will be inversely proportional to the absolute temperature of the black body. And this is called the Wien's displacement law. And you know why it is displacement, because you lowered the temperature and the peak wavelength shifted, or you increased the temperature, the peak frequency shifted. So this got displaced, and that's why there is displacement law. We discussed this, and these are known. You know these from your thermodynamics class, so I'm not going to too much into the details of this. And I already explained them in my previous lectures. So let's start. What we want is to calculate this thing, this U nu, d nu quantity, okay, and plot it from theoretical perspective. So what we want is a function of frequency, d nu. That function we want to calculate from physical assumptions, considering physics, and mathematically we want to find this function that will explain these data points, that will fit perfectly over this data point if plotted, okay? So classically, Rayleigh-Jeans tried to do that. So their approach can be broken into a few steps. First of all, goal. The goal is to find out this thing, which is spectral energy density, energy radiated per unit volume in the frequency range nu and nu plus d nu, in this range, okay? Which of course corresponds to some wavelength range, lambda and lambda plus d lambda. In order to do that, first thing we need to understand is one. The black body can be approximated by a cavity with a small hole, small opening. The cavity has perfectly reflecting walls inside, okay? So if any wave, any electromagnetic wave, that is light, enters this hole, it starts getting reflected by the perfect walls, perfectly reflecting walls. We'll just keep doing this. And so on. So it will go on forever. And maybe so any colored light, any wavelength, it just, whatever enters, it gets trapped in forever reflections. And that's why it's equivalent to a body, this hole actually, not the whole cavity. This hole is equivalent to a body, a black body that absorbs any color. So a study of this opening, a study of anything coming out of this opening, any radiation coming out of this opening is like black body radiation. So this is first assumption. And that's what experimentally also been used. Second, so first, cavity. Okay. Second, waves inside the cavity will of course be in standing waves. You know what standing waves mean. If you had two walls, reflecting walls, waves can exist only either like this, or this, or this, like that. The amplitude becomes zero at the wall. Okay? You also know this from strings. If you have a string tied at its two ends, it can vibrate either in the lowest mode like this, or like this, or like this, sorry, and so on. Okay? Higher and higher frequencies can exist, but the endpoints must be nodes of the wave. What that means, you already know this again from your waves and oscillations, that if L was the length of this particular cavity, let's say one-dimensional, I'm considering for now, then this L must be equal to an integral multiple of lambda by 2, half wavelength. So first half wavelength, half is equal to L. Then there are two halves. Then there are three halves. So basically, integral number of lambda by 2 will be equal to the length of the cavity. This is the condition of standing wave. And the assumption is that the waves that are inside the cavity are in standing waves mode. Standing wave. And the condition for a one-dimensional standing wave is that if L was the length of the cavity, then L must be equal to n times lambda by 2. Or simply n equal to, let's say, 2L by lambda. Now, if we consider a three-dimensional cavity, that's our case basically, three-dimensional box, let's say, is our cavity with a hole somewhere here. Anyway, this is our cavity. Then we have basically three directions, X, Y, and Z. And in any direction, there will be, so in X direction, this wall and this wall. So waves can exist in standing wave mode between these two walls. If we consider Y direction, then this wall and that wall will again have have some standing waves between them. Similarly, in the z direction. Okay. So independently, this must be satisfied in all three directions. What that means is there will be some nx will again be 2lx by lambda. If we had like the length of this box was lx and ly and lz. Similarly, this nx again is an integer, so nx equal to 0, 1, 2, etc. Similarly, in y direction, another condition will be ny equal to 2ly by lambda, and in z direction, nz equal to 2lz by lambda. Three independent conditions. And if you did your waves and oscillations correctly, or like rigorously, then you know that the condition of standing waves happening in any arbitrary direction inside the box, any arbitrary, not like a standing wave absolutely in the x direction or absolutely in the z direction, y direction, or absolutely in the z direction, then you know that for any arbitrary direction, the condition that must be satisfied is nx squared plus ny squared plus nz squared equal to 2l over lambda whole square. Here I have considered a cube for simplicity. So lx equal to ly equal to lz equal to l. So it's a cube of equal sides, okay? L. So this must be the condition that has to be satisfied for standing waves inside a cube of length L. This is important. We'll be using this later, a few minutes later. But just for now, try to recognize what this is geometrically. This is some variable square, some other y variable square, some z variable square, equal to some constant square. This is pretty much like x squared plus y squared plus z squared equal to some r square, a sphere, okay? In xyz space, a sphere of radius r. In this case, in nx, ny, nz space, a sphere of radius 2l by lambda. And what nx, ny, and nz are? They are they're integers. But, I mean, look at them. They can start from 0, but they cannot be altogether zeros, because then everything is 0, and that just means that there are no waves, okay? So at least one of them has to be non-zero. So if you consider like nx equal to 0, ny equal to 0, nz must be at least 1 or any other number, not 0. They can be 0, but not all of them 0 at the same time. Anyway, so this is a equation of a sphere in this space of, if you had a space with direction like nx, ny, and nz, then it's a sphere in this space. But one important thing is that it's not a usual space because it's not continuous. Because in usual space, x can take any real value. It can be 0.1, 0.001, 1000, 0.01, or anything. But here, because these are integers, the only allowed values are integers. 1, 2, 3, 4, 5, and so on. Y also 1, 2, 1, 2, 3, 4, dot, dot, dot. And in z direction also 1, 2, 3. So what that means is this is a spherical equation of a sphere, but it's not a continuous sphere. It really can take values like this, these points, or in this. 0, 1 would be here. So 0, 0, 1 would be this one. 1, 1, 1, 1, 1 would be somewhere here, up, like that. I mean, it's a space that is not continuous, but filled by these numbers, because your x's are actually integers and not a real line, so real in real numbers. So nx and ny and nz cannot take any real values, they just take integral values, integers. Okay, this is important because we are going to use this later. So, standing waves was the assumption. We will need that. Why? Because the energy that we are going to calculate are basically distributed in those waves, and those waves are in standing waves condition. Okay, the standing wave states. Third, to calculate the energy, to calculate an energy between wavelength range lambda and lambda plus d lambda, we need to count how many standing wave modes are possible within those frequency range. Because, for example, let's again take this one-dimensional case, okay? You can have this standing wave, you can have this standing wave, you can have this and so on, maybe some higher state like this, so on, right? And then some other higher, okay, very higher frequency, and so on, forever, very high frequency. We're interested in a range. Let's say we want our frequency. So let's say this one is lambda 0, this one is lambda 1, this one is lambda 2. I'm just naming them, okay? The next one. Lambda 3, let's say, and so on. So asking that what is the energy radiated in the range lambda and lambda plus d lambda, and I have to know how many, let's say if this is our lambda, particular lambda, and let's say here we have lambda plus d lambda, then how much energy is radiated in this range? We need to know how many standing waves possible between these two bars. And then if we know energy of each of these standing wave, we multiply by the number of waves possible and we get the total energy radiated in this wavelength range. And so it's a problem of counting the number of possible waves. So the next point is counting the number of standing waves or normal modes. So counting the number of modes. So it's a problem of counting, and that's where we'll need some geometry. Let's say once we counted and we say that number, so number of waves is given by some g lambda d lambda. We can then use the relationship between frequency and wavelength, you know, velocity, speed of light c equal to lambda times mu, and we translate this equation into an equation of frequency, so it will become g nu d nu. That will be our counting, the number of state between these two frequency range. The next step would be average energy carried out by one such standing mode. So basically average energy per standing wave, we have to know that. Once we multiply this by the total number of standing waves in that range, g nu d nu, what we find is the energy radiated, total energy radiated in that frequency range, and we call that small g nu d nu. Sorry, we call that u nu, d nu. And somewhere here, we have to divide this by total volume to get, the density per unit volume. We'll do that. And then we'll be done. Okay. So until this point, everything is fine. We have to now start counting. So the standing wave condition is that these integers must satisfy this condition. We can simply write this thing as sum n square. So n square equal to 2L over lambda or square, or n equal to 2L over lambda. Okay, where n is equal to square root of nx square plus ny square plus nz square. Now, okay, so we need to know how many standing waves are possible in the frequency range lambda and lambda plus d lambda. Now look at this. 2L over lambda is our radius of the sphere in the nx, ny, nz space, okay? Let's consider for simplicity two-dimensional case. We have nx, we have ny, and obviously 1, 2, 3, dot, dot, dot. 1, 2, 3, dot, dot, dot. Only these values are allowed. And so in this space we have just points, allowed points. Any point here and here are not allowed because it has to be integer value in each direction, x and ny. Like that. For example, something here will be 1000 and here maybe 1001. But, there have to be some integer. This is my space. Now, if I take a particular value of lambda, that will correspond to some nx square plus ny square plus nz square, which means some value of n. Some value of n. That is our radius, constant radius. So it will be a circle, because for a constant radius, this could be 0, this could be, let's say, 1, and this could be 1, or this could be 1, this could be 0, and this could be 1, or this could be 1, 1, 0. Still, they will satisfy a constant radius 1. So for some lambda, we will have such fixed radius, some fixed, circle, and for various points, so various combinations, like this value is also, this value is like some, let's say 100 and 1. So 100 comma 1 satisfies this equation for this particular radius n, let's say. Okay, nx squared plus ny squared plus nz squared equal to n. But some other value, this one, which is 3 and some 1000, let's say 3 comma 1000, also satisfies this same radius n, and therefore we will have a circle, right? We'll have a circle. Which means that a lambda, a particular lambda, corresponds to a particular n, okay? A particular lambda correspond to a particular n. And then we're talking about lambda plus d lambda, the range. So lambda plus d lambda will be again another radius. And for that, it will mean some n plus dn. Okay, some n plus dn. And that will be another circle. That will be our dn, some dn. And so this will be n plus, use another color. This will be our n plus dn. So this will be corresponds to some n plus, this will correspond to some n plus dn. So we are then talking about, so when we are saying how many waves are possible between the wavelength range lambda and lambda plus d lambda, we're basically asking how many points are within these two circles, okay, in 2 dimension. This is 3-dimensional case in the end that we will come to, but for now, for simplicity, we're talking about this 2-dimensional case. How many points fall within these two circles? Those will satisfy this lambda and lambda plus d lambda condition. Within this range, we are interested in the waves that fall within this range, and they correspond to particular these numbers, and these particular various numbers will correspond to these various points. So we need to count the number of these points, and once we do this counting of the number of points within these two circles, we are done. We have already counted the number of waves that fall within the range lambda and lambda plus d lambda. Okay? Now, here comes an approximation. So, this we can understand easily, that if we had increased this d lambda, like we had taken this bigger annulus, right? This big circle and the other circle is bigger. Then there will be more points. If we had shrunk the area, then there will be less number of points. So basically, the number of points in the range, the number of points, would be proportional to the area that we consider. It will be proportional. Yes, but we could actually say that they're almost equal. We can approximate that the number of points within is actually equal to the area of this strip. If these points were really, close to each other, very dense, if that was the case, then this would be true. And just remember that when that happens, that happens when these nx, ny, and nz are large numbers, large, thousands and thousands, maybe millions. And then, like choosing this 1 million, and this is 1 million and 1, and this is let's say 1 or 2, then changing a little bit around this 1 million, you will get really dense points here. And these points will look like almost, continuous. And at that point, the number of points will be almost equal to this area. Now, can we make that assumption that really the points are that dense? Actually, we can. We can if we say that our size of the cavity is much larger than the wavelengths of the waves inside. Why? Well, that would mean if your wavelength is this, then how many? 2, 3, 4, 5. 5, and that means 10 half wavelengths will form a standing wave. But if your cavity was really large compared to your wavelength, then we would have waves like this. So maybe you know wavelengths are in nanometers also, and if this is in centimeters, that's still like, 10 to the power 9 nanometer, and this cavity in 1 centimeter, so that will be 10 to the power 7 waves possible within this cavity. So it's a huge number of standing waves, and that means huge in number, these n, x, and y, and z. And that's the assumption actually. The size of our cavity is big enough, and then we can equate that the number of points within this is the number of points within this strip, within this area, can be equated to the area, and we are going to use it. Okay, so in this two-dimensional case, what is the area of the strip? Now remember, why we did not draw this full circle? Because that's not allowed. Remember that the nx, ny, and nz can take only values starting from 0. They cannot have values like -1, -2. So only positive numbers. So starting from 0 only in this direction, starting from 0 only in this direction, starting from 0 only this direction. And therefore, in two dimension, there will be 4 quadrants, and so we have to take 1/4 of the area. Anyway, the area of this strip would be the perimeter, the length of this, which will be 1/4, because we are taking only 1/4 part, times 2 pi r. So what is r? In our case, that's n. This is the length times the thickness, dn. And that will be our area of this particular strip. If we move now to the real case of our three-dimensional cavity, then that's just, this circle moving out like that, becoming a sphere. So then we have these spherical shell confined to this particular quadrant. So there will be 4 quadrants up, 4 quadrants down, so total 8. We have to now take 1/8 of this thing. And now the area becomes a volume. So the number of points within the spherical shell can be now equated to the volume of this spherical shell. So the number of points, n, equal to, let's say dn, equal to the volume. So 1/8, of course, because 1/8, only the positive numbers. What is the area of this particular shell? 4 pi radius squared times the thickness, dn. And that's it. That's the number of points. That's the number of standing waves. Now, these are electromagnetic waves. That means one wave is actually 2 perpendicular waves. Electric field fluctuating in this direction, and exactly in perpendicular direction, magnetic field oscillating in this direction. So that means 2 polarization states. So one standing wave is basically 2 standing waves, okay, for electromagnetic waves because of polarization. So actually that number gets doubled. And we denote this number by G n dn equal to, so 8 and 8 gone, pi n square dn. Done. This is, of course, in terms of n. Now we have to translate this from n back to lambda. And we know how, because n equal to 2L over lambda. N equal to 2L over lambda. And wait, finally we have to translate it back to frequency. We can do that already. So c, the speed of light, equal to lambda nu. So 1 over lambda equal to nu over c. And let me take it back here. So n equal to 2L nu over c. And that means that dn equal to 2L over c d nu. Right? Therefore, finally, our counting is really done. So the number of waves within the frequency range nu and nu plus d nu is pi n square. N is 2L nu over c, n square dn. dn is 2L over c d nu. Well, that just becomes 8 pi by c cube nu square L cube d nu. Now the next step is just taking the density. So the density would be dividing by volume. What is the volume of the cube? Is L cube. So we divide by L cube. So the density, spectral density, just let's call it spectral density. So number of standing waves between nu and nu plus d nu per unit volume is just g nu d nu divided by the volume. So we get 8 pi over c cube nu square d nu. That's our g nu d nu. Till now, up to this point, there was nothing classical much. Mechanics I'm talking about. Waves were there, but that's fine. Or nothing quantum. But after this step, we actually move on either in the quantum direction or in classical direction. But this is where we pause for a moment. There is nothing energy here. Let me write it down. So we are at the step of just spectral density. Nothing, no energy. So it's not spectral energy density, it's just spectral density. Now, if we knew the average energy per standing wave, how much the average energy of a standing wave was, we could just multiply it. Let's call that epsilon bar as our average energy per standing wave. Then multiplying this with this would give us the actually spectral energy density. The energy radiated per unit volume in the frequency range nu and nu plus d nu. Here comes the classical derivation. Law of equipartition of energy. Law of equipartition. Equipartition. You know this very well from your last semester thermodynamics. In fact, I explained this in the last part of our semester, that according to classical mechanics, every degree of freedom gets half kBt amount of energy. Kb is the Boltzmann constant, T is the temperature. We are doing all these calculations at a particular fixed temperature. Remember that. The cavity is maintained in a particular fixed temperature T. Those walls have molecules, oscillators, they're oscillating at a particular temperature T. Now, law of equipartition of energy says that per degree of freedom gets half cavity amount of energy. Now, here's the thing. A harmonic oscillator has 2 degrees of freedom. A harmonic oscillator, its energy can be written down as half k x squared plus half m v squared. Its position is in quadratic form, its velocity is in quadratic form, and therefore it has 2 degrees of freedom. And because it has 2 degrees of freedom, it gets half cavity and half cavity, and therefore total kBt amount of energy. Therefore, a harmonic oscillator gets kBt amount of energy. One harmonic oscillator oscillating in a particular frequency. Now, why am I talking about harmonic oscillators? Well, the cavity that we consider, the black body, the hole, these walls of the cavities have molecules, okay? And they're constantly oscillating. Some are oscillating slowly, some are very fast. So they're absorbing this particular frequency and at the same time they're emitting them. And therefore, the energy that we are considering, the energy of the waves, are really coming from the energy of these oscillating states. So a molecule is oscillating like this. It's receiving a standing wave, so it's receiving energy from the wave and it's giving off the same radiation. So it's basically, in equilibrium with the environment. So an oscillator is absorbing a wave and at the same time releasing it. So the oscillators are in equilibrium with the standing waves. Therefore, the energy per oscillator that are actually generating these waves per oscillator is kBt. And therefore, the energy, average energy per standing wave is exactly kBt. So our epsilon bar, that is energy per standing wave, becomes kBt. kBt. And therefore, the final step is the spectral energy density. Spectral energy density, or U nu d nu, equals the spectral density, number of waves in the frequency range nu and nu plus d nu, times the energy per standing wave, epsilon bar. And that is equal to kBt d nu. This is the final theoretical result according to classical physics. So we found the function, the theoretical function. We said we wanted an f nu d nu, and we found the f nu. What is this f nu? It is these constants This is a constant, some constant, 8 pi by CQ kBt times nu square. So nu square, that's the function. Now, does that explain our experimental data? How did the experimental data look like? Nu, you knew, they knew. When we plotted using our experimental table, the data looked like this. Remember? Well, of course, this cannot explain this data because this is just a nu square function. So in nu space, it is a parabola. It's a parabola, so it's a quadratic function. Maybe at the beginning here, it can explain a little bit, and then our theoretical function just shoots up towards infinity. But the reality, the data, looks like this, a function that must come down, must be bounded. This is where the classical physics fails. It cannot explain. And another weird, strange prediction of this classical physics theory is that, for example, consider a piece of iron. You have heated it up, so it's now radiating in red color, let's say. But it really is, as I told you, radiating in every color, right? So you want to calculate the total energy radiated by this piece of iron. So you have to, of course, sum all the energy radiated in all possible frequencies. So what do? You have to integrate 0 to infinity and your u nu d nu. So you have to integrate over all frequencies, and then you have got what is the total energy radiated by this piece of iron. What happens when you do that? If you put this function, some constant that will come out here we'll have nu square. And that's obviously infinity. Integration of nu square, d nu. That's like area under this curve. So as you go higher and higher in frequency, the area is just increasing, becoming infinite. It's not bounded. So just a piece of iron is radiating infinite amount of energy. We could use this piece of iron to power up the whole world, and our power energy solution will be solved. That's obviously nonsense, right? And that's why this is called the ultraviolet catastrophe. Ultraviolet because higher frequency. By ultraviolet we mean higher frequency. At higher frequency, this theoretical result blows up. Doesn't make any sense. So it's a catastrophe at ultraviolet. By the way, this result was due to Rayleigh and Jeans. So it's called Rayleigh-Jeans law. Now, that was the end of 19th century. End of 19th century. 1890s, okay? Planck was really disturbed by this. Planck was really disturbed. Max Planck. He wanted to explain the real data. That looked like this. So obviously the real physics, if there was one behind this, if we discovered, would give us a function f nu that when plotted should look like this. That would explain the real data, the real experimental results, f nu. Planck didn't know what physics was behind this, but he was a genius, he was clever. He was able to guess the function. So remember that our counting was fine. The counting was absolutely fine. The counting was G nu D nu. That involved no quantum, no classical physics. Just counting and waves, of course, waves and oscillations. But no mechanics of energy, like average energy calculation. Up to that point, we had 8 pi by c cube nu square d nu. That's fine. Our next step was the u nu d nu, and that was this just g nu d nu times this epsilon bar, the average energy per standing wave. So up to this point, it's fine. Something wrong with this part. Okay? So he thought, what function, if I guess a function, what would be that function of nu that will explain this data? Obviously, this epsilon bar will have to be a function of nu, because if it is not a function of nu, then the final function will be again nu squared, just a parabola. So we need this nu bar to be something that when nu increases, this parabola goes on, but then something here will pull it down. So this one wants to go up, nu squared, but this one will first be, polite, but then at some point it will start pulling it down. It will pull it down, this function, and will become like this. So this function has to be something that after some time starts decreasing rapidly, that will pull down this nu square. And he guessed it. He guessed this epsilon bar to be h nu over e to the power h nu over kBt minus 1. But this h is just a constant. You don't know what the value of the h is. Boltzmann constant temperature, nu is the frequency, and fine. But h was just a proportionality constant. It was needed because if you take some value, so if it was like this, so he knew that the function should look like this. But then the function could be this, it could be this. So he put a constant here. And he adjusted the value of h. So he adjusted the value of h. It was 2 less, then he got this, this plot, Then he increased it and he got this one. So at perfect tuning, when he did a perfect tuning, he was like, increase this slowly, and he found exact match with the data. And that tuned value of h turned out to be around 6.625 into 10 to the power minus 34 joules second. That was the value of this proportionality constant that we now is known as Planck's constant, celebrated Planck's constant. Anyway, this guessed function was inserted here by Planck and he explained the data. But even then, he had no idea what it meant. Where is this function coming from? Which physics this function is coming from? It was just a mathematical guess that would explain the data. But what is the physics that is giving this function? Okay? That's really where he got stuck for weeks. He thought deeply. It was, as he said, the most intense time of his life. Many weeks. Then finally he realized where this was coming from. He realized that, remember again, the oscillators of the wall that are vibrating. He realized that if those oscillators were not allowed to, absorb or emit energy of any amount, but some particular amount in the form of packets. So he said, if the oscillators had energies defined by En equal to NH nu, where n equal to 0, 1, 2, 3, and so on, if the energies of those oscillators existed only in these values. An oscillator could oscillate with this energy h nu, or with an energy 2h nu, or 3h nu, but the oscillator cannot oscillate with an energy corresponding to, let's say, 3.5 h nu, cannot, only in this way. Then if you apply statistics, I mean, if he, not you, he applied Maxwell-Boltzmann distribution law to these oscillators, and if you calculate the average energy per oscillator using this, that the oscillator can have only energy in the form of nh nu, where nu is the frequency of the wave that they are giving out or absorbing, and the distribution law, if you apply MB distribution law, then epsilon bar, the average energy per oscillator, comes out exactly to be h nu over e to the power h nu over kBt minus 1. And that, of course, explains the black body radiation perfectly. And this is where quantum theory comes in, because quantum means how much. In Latin, quanta means quantum, means how much. In Italian, for example, quanto means how much, means kiman, koto in Bengali, for example. So it's a piece of energy, one packet of size h nu energy, 2 packets, 3 packets, 4 packets, not 1.5, not 0.3, 0.5, these are not possible. Only integral amounts of packets of energy, quantums of energy. He called them quanta, but for now we know that this quanta of electromagnetic wave is now known as photon. That was exactly 1900, the beginning of quantum theory, the quantum revolution, let's say. Thank you.